I think we'll get started here. Welcome everyone to today's InfluxDB IOx Tech Talks. My name is Caitlin Croft. I am super excited to have you here today. We'll just give our friends a couple more minutes to join. I know that not everyone joins right at the top of the hour. I love that you guys do. But just want to go over a few friendly reminders before I hand it off to the team. So the session is being recorded and the slides and the recording will be made available later today. You'll be able to find the recording on YouTube, and then the slides will be available on our website as well. Please feel free to post any questions you may have for the team related to what they're talking about today, or if you have other general InfluxDB IOx questions, feel free to post them in the Q&A or the chat, and we'll be sure to answer them at the end. We have lots of different events here at InfluxData, so if you're interested in learning more about how to use our product, or even learn about how other customers are using it, be sure to check out our website. We actually have a product training, an InfluxDB Cloud product training at 10 a.m. Pacific. So just here in a couple of hours. So if you're interested in joining us for 2 webinars today, more than happy to have you on both events. We also have our biannual Influx Days coming up here in a couple weeks. So yesterday and the day before, we had the Flux training component of the event. And then on the 26th and 27th of October, we have the conference part. So it is completely free. It's obviously completely virtual. So be sure to check it out. Jacob Marble, who is part of the InfluxDB IOx team, will be talking about InfluxDB IOx and open telemetry. So there are some IOx specific sessions, and then some other really fantastic sessions from customers like WP Engine and Red Hat, as well as keynotes from Paul, Dix, and Tim, and a bunch of other engineers at the teams here at Influx. So it'll be a really great event. I hope to see you all there. Super excited to have you there. Without further ado, I'm going to hand things off to the team. Andrew, I know you have slides ready to go, but I also see Paul here, not to put him on the spot, but Paul, are there any opening remarks or comments you'd like to make before we get started?
No, nothing specific. Just thanks for joining in, everybody, and enjoy Andrew's talk.
Cool. Well, off to you, Andrew.
All right, well, thank you for joining. Today, I'm going to talk about query processing in IOx. And I just wanted to preface this talk with, right now, this is probably, like, the details of this talk are probably relevant to the number of people you could count on a single hand. However, I think sort of just by giving the overall understanding of how query processing works in IOx and how we think about it and what some of the decisions we are made, I'm hoping you get more of a sense of that. And if you're interested, you can watch, look at more details. So, but anyway, today I'm going to high level review of query processing, and then also dive into some of the details. Just as a reminder, my name is Andrew Lamb, like Caitlin mentioned. I'm currently on the IOx team. In the past, I've worked on query optimizers and other database systems. And I've also spent my time doing more sort of cat wrangling as a chief architect, VP of engineering kind of roles. So I'm super excited to be back down in the guts of working on databases and query engines again. Today, I'm going to talk largely about the query engine, but I'm going to start with explaining what that is. I've done a couple other talks in the past, if you're interested, about data fusion and what a query engine is, like sort of the high level view. But in order to understand, really what a query engine is, you need to understand the data storage model that the system that it's operating on uses. So I'll review that briefly. Then we'll talk about query processing at a high level of in IOx, and then we'll jump down into low level details. So hopefully you'll find the first part interesting, and then if you're still with me at the end, perhaps you get something out of that too. So again, this is a brief reminder of how IOx stores data. You need to know this because primarily what a query engine does is it connects the request for what a user is asking for, and me something about my data yesterday grouped by such and such. And the query engine's job is to translate that user request down into actual scans and calculations on data. So one of the primary value adds of a query engine is that it maps the user query into the actual sort of physical structures that the database is using. So the query engine and the data physical structures are quite closely tied. So that'll feature prominently in this talk. So IOX's primary data model is the data it's a relational model, and it is that each I'll talk about measurements in a moment, but basically it has tables. The data is broken up into tables as in other databases. Within those tables, data is partitioned. We would call it horizontally partitioned, so that means some subset of the rows are kept separate. Typically, that partitioning is done by date, some kind of date or time partitioning, and then within each partition, there's a bunch of chunks. So I think that's pretty much what that text says. So you've got tables, partitions, chunks. Again, that's important because the query engine effectively is operating on the chunk level, so you got to understand that how that chunks maps back to what users cared about. When I was talking about chunks is the physical unit of organization within IOX. I think we probably have a whole other talk in the works to sort of review what both the original plan for data layout, and then also sort of how it's evolved as we've been going. The implementation's been underway. But in IOX, as a reminder, data gets ordered in chunks. This is all within a partition, right? So data comes in. As data is written in, it gets written into the open chunks. Older chunks are closed. And in this case, IOX spends a non-trivial amount of complexity remembering which chunks were created before other ones. The reason it needs to do that is because new data can be written in that effectively updates the old chunks, but yet the old chunks are never actually physically modified. So again, it's up to the query engine then to resolve the different inputs, inserts, deletes, and data to produce the correct answer, even though the chunks themselves might very well have overlapping or deleted data. Talked about all that stuff. And the final sort of part of my introductory session on stuff you need to know about the data model is, if you've worked with Influx before, you'll be familiar with what's on the top right here, right? You've got, this is InfluxDB line protocol. So Influx line protocol has a measurement part to it, so that's in blue. Then it has a set of tags, which I've circled here in red. Then it's got fields in each row, each line, then it's circled in green, and then a timestamp in yellow. And you'll note that each one of those components has a mapping into IOX. So in this case, the measurement actually is the table. So depending on the measurement you insert, that's the table in IOX that gets written. The tags are stored as columns. So you can see these tags, location shows up as a location column. The two fields, in this case, temperature and humidity, likewise are stored as columns, as is the timestamp. Now, this is important because the write path, which again, we'll probably have a separate tech talk about, is responsible for translating when data comes in this line protocol format, translating into the relational table format that I showed you here. However, IOX also allows people to query the data as though it were stored in the InfluxDB data model. So the query engine is also responsible in times for basically translating queries that are in terms of tags and fields and timestamps and measurements back into scans of the underlying chunks that were organized by table and partition. So that's why I'm trying to give you this overview, because again, this is like part of what the query engine exists to do, is to bridge the actual physical storage of data with the query, like the queries that people want and the logical views on top of it. So with that as a introduction, which might or might not have been interesting to people, I'm now going to move on to talking about query processing in general. So the first thing, I had to have an obligatory one-ring reference here. The goal, at least from my perspective in IOX, was to have one execution engine. So what do I mean by that? So the write path, as data comes in, writes into this open chunk. But as soon as the open chunk becomes closed, then we wanted to use the same system anytime the data in those chunks was read, right? And so queries are clearly an example of that, where the user's asking for some subset of the data sliced and diced a particular way. But also if we're going to do things like rewrite the chunks or compact them or persist them, again, becoming topics probably in a subsequent tech talk. We want to use the same sort of system, it's part of the query subsystem, in order to do that, rather than having multiple different systems. And the reason we want to do that is so that we reuse the existing execution machinery as much as possible. So that might not, it doesn't seem like initially at first that like compacting a couple of chunks necessarily needs the same level of sophistication as query processing. But I think you soon find that you'll want to do streaming execution, aka batched, so you're only processing little chunks at a time. You want to have separate resource management and worker pools potentially, and memory limits and whatnot. It all ends up being very, very similar. So rather than implementing it twice, IOX's goal is you have once, and we run both the reorganization plans plus the query plans through the same underlying system. And I think the other thing that is very important when we're designing this query system is to take full advantage of InfluxData's historical contribution of belief in open source. So we both contribute significantly to open source projects, and we also want to be able to amplify that investment by leveraging the contributions from open source back. So obviously IOX is all done open source, but also it was very important to design an execution engine to try to be able to harness that open source, the good open source, both karma and contributions that come back, as we contribute upstream as well. So that leads, it won't surprise you in the least probably if you've been following IOX, you've listened to my other talks, or you read Paul's original blog post about IOX, is that all the queries run through a unified planning system that is based off Data Fusion and Arrow. What that means, if you're a Rust connoisseur, which I have no idea if you are or not, at the end of the day, what that system lets you do is you can end up with these asynchronous streams that fits nicely into the Rust async ecosystem. You can use the fairly sophisticated Tokyo executor to run them and control the resource usage as it goes. So that's like the high level design. Is basically we're going to run all chunk reading, data and chunk reading through a unified planning system. So now how does that actually look, and what am I talking about? So if you think about query processing, IOX has three major operations that can touch data that's stored in chunks. It's got what's called the storage gRPC. I call these front ends. So these are the types basically of queries that the system can handle. So there's what's called the storage gRPC front end. So storage gRPC is the internal implement API that Flux and InfluxQL use to talk to the storage engine layer in InfluxDB. And so IOX can also talk the same protocol, and it's basically a query language. I'll describe it in more detail later. We also have a SQL front end, which it means you take SQL, queries as SQL strings, and then you're able to generate queries from them. Then we also have what's called the Reorg front end, which is certain operations within IOX. Again, I'll talk about those more in detail later. Certain operations within IOX want to read and write and modify, well, not modify chunks, but create new chunks. So we've got those three inputs. The way the unified query plan that I was just talking about is shown here is that, sorry about the formatting, that all of them use the same intermediate format. In this case, what's called the Data Fusion logical plan. So each of these front ends generates the same data structure, again called Data Fusion logical plan, which I've talked about in past tech talks about Data Fusion. Those are then run through the standard Data Fusion query processing pipeline. And so there's a bunch of optimizations, which I'll talk a little bit about. Then it goes through a physical planning operation, then finally execution operator that actually sort of reads data, applies filters, does grouping, that sort of stuff. And at the output, you get these record batch streams that I talked about. So you get sort of batches of rows that come out. And then depending on how the query went in, the different queries have different ways that they expect their outputs. For the storage gRPC, it expects a certain gRPC formatted response type. So we have code that translates record batches back into there. For SQL, we've chosen to use what's called Arrow Flight, which is another part of the Apache Arrow ecosystem, which is a way to transfer result sets back to the requester directly using arrow arrays without having to translate it to some other data format. And so this shows sort of another reason why being aligned with the Apache Arrow ecosystem is bringing us benefits. The same internal format that we use to actually execute the plans, we send the results back the exact same format to the clients. So without having to spend any time translating the data formats. And then inside these compact plans, you get 2 streams, and then we have specific code that'll actually write that either to a read buffer or a Parquet file. So when I'm talking about unified query system, this is what I'm talking about. Is we want to reuse all this middle stuff, and then we only have the parts that are specific to the different types of queries. So I'm going to talk a little bit about each one of these different front ends in depth, but I'm going to probably stop mostly at the logical plan. We'll talk a little bit about physical plans at the end. So query optimizer features, right? This is typically bragging rights for every query engine, right? You read anything about Spark or any other modern query engine, they'll talk about the variety of optimizations the query optimizer does. I think it's actually one of the main values of a query optimizer, right? Especially for things that are what's called implementing declarative queries. So that means the user, in this case, like as a SQL query or as one of these gRPC storage queries, it says what they want, what data they want, and then it's up to the system to go figure out how most efficiently to get it, right? So that separation between the what you want and the how to go evaluate it is the play that the typical query optimizer has to play with. So there's a whole bunch of there's a whole research literature for classic optimizations that I would talk about that we very much leverage data fusion for. So that's stuff like projection and filter pushdown. So projection pushdown is a fancy way of saying only select the columns that you that actually appear in the output. Right, but there's a variety of other sort of fancier things too, where there's partial evaluations of predicates. Like if you say where the state is equal to, I don't know if the state's equal to Massachusetts or the state's equal to New York, and some other columns not equal to false or something. If you're most query optimizers will partially evaluate that expression. So there's a whole separate talk I talked a little bit about in the data fusion talk, but there's a whole bunch of existing optimizations that happen within data fusion, and IOx gets them for free in all the different types of plans, right? Not just SQL, but the gRPC plans and actually also the reorganization plans. There's predicate evaluation during scan. Actually, data fusion doesn't have, data fusion kind of has that. IOx definitely has it for read buffer evaluation, and it's put a lot of work in there for mutable buffer and Parquet. It's kind of there. The real key in the read buffer is that we avoid having to materialize results, right? The read buffer stores data in a very compressed format. The ideal evaluation for predicates is that you don't have to decompress the data to apply the predicate, because typically you'll throw a lot of the data away. So IOx definitely has that. We have chunk pruning on predicates so that we can look at the list of chunks, right, that I was talking about earlier. Tables are divided into partitions, then divided into chunks. Chunk pruning says each one of those chunks has metadata about its columns, like what the min and max values are. And so if you say, I just want data from, tell me something about the last hour, and your query has predicates on the time column, IOx will then go and not even, it won't even look at chunks that have data that's older than that. And it can just prune out a huge amount of the data right away. That's also one of the key ways we plan to be able to offer unlimited retention effectively, right? You can have giant numbers of past historical chunks, but most queries will be able to rule almost all the chunks out very quickly just on metadata alone. So you have a huge amount of data in the back, but it doesn't really matter. Within a Parquet file, you also have horizontal chunks called row groups, which we can use to further reduce the IO required. We do that leveraging what's in data fusion, and then grouping aggregate pushdown. I'm sorry, the text doesn't quite align with the numbers, but grouping and aggregate pushdown is something we don't currently have. That's I would say one of the more advanced optimization and transformations that query optimizers will do. We don't have it. Data fusion doesn't have it yet, but it's definitely on our thoughts. And what our thought would be is we'll add it to data fusion, and then we'll get into IOx that way. So if you're paying attention, in my mind, this is pretty full featured list of optimizations for a query optimizer. So I think this is pretty good. Now I'm going to switch modes a little bit and talk about the different front ends and what they are, and maybe give you some sense of like why they're needed. So we've got the SQL front end. So in this case, as I was mentioning, this is like the user wants to run a SQL query. The way that works under the covers is we use the Aeroflight API. There's a flight client in IOx. That flight request is sent. Flight happens to be implemented on top of gRPC, so it's sent as a gRPC encoded request to IOx. Happens to be on port 8082 if you care by default. IOX's query engine, in a way I'll describe in a few minutes, then turns around and combines the data from Parquet files in the read buffer and new buffer and sends the responses back via flight gRPC again as arrow buffers back to the client. So that's what the SQL front end and how it's used. So if you like use the InfluxDB IOx command line to run SQL, this is what's happening under the covers. Now the logical plan, I'm not going to talk a huge amount about this, but there's I said the input is a string that looks something like this, perhaps. The output of the front end is a logical plan. I'm going to use the same sort of types of pictures I used in the talk about data fusion, but just to remind those of you who didn't see that scintillating talk, which I realize is somewhat esoteric for most people. You read these plans, probably like this talk, is you actually read these plans bottom to top. So this is a table scan, right? I'll talk about data fusion and IOx, but in general, this is how most data, like if you read database query plans, this is what they look like. So they typically are like trees, they're rooted. The leaf at the bottom is a table scan or some kind of source of data. So in this case, it says, pick me all the rows from the CPU table. Then there's nodes that each apply relational operators. So you could think about sort of streams of rows flowing between these operations. Then these blue boxes represent transformations from one input table to another output table. And they do different things depending on what the query calls for. So in this case, we have a scan, a filter, and then a projection is a fancy thing that just fancy relational algebra word that just means pick some subset of the columns or possibly an expression. So this string gets generated, this logical query plan, and then that gets sent down through the rest of the data fusion execution machinery. Now, as I mentioned before, I think the actual SQL planner in IOx is about 10 lines long, and all it does is call the data fusion one, right? So we totally sort of punt all the SQL planning to data fusion, and it works quite well. It's some IOx specific stuff. While the logical plan has we reuse what's in data fusion, the actual underlying sort of provider for where that data comes from is our own code that we've used the data fusion extension points to expose. So basically, when it says table scan CPU, eventually, in a way I'll discuss at the end of the slide, that turns into scans of the multiple different chunks. IOx will then also apply upserts, right? So it would deduplicate any data that's required, apply deletes, and provide it up. But the logical plan is the same, which I think is kind of cool. So we can reuse everything in data fusion. So now I'm going to move on to the second front end. If you remember, there's three front ends. There's the SQL front end, the storage gRPC front end, and the reorg, the lifecycle planner front end. I'm going to talk about gRPC last because it's the most complicated, most specific thing in IOx. So the reorg plan, this is when, again, the lifecycle planner, which also should be probably the lifecycle policy manager, which should be another future IOx talk at some point, decides to either compact chunks, so that means merging multiple chunks together, or persisting them. It has to read data out of the chunks, apply any deduplication to resolve upserts, and then also apply deletes before we write the new chunk. So the way, so compact is one of the types of plans that can be created. So that just gets given some number of chunks on the input. The compact plan will then, as I mentioned, resolve the upserts and deletes and produce this record batch stream out. There's a slightly modified one. It's for the persist operation. So persist is the term that's used for writing Parquet files into object store as part of the lifecycle policy. The actual plan that's used for there is it's called a split plan. It basically is the same as a compact plan in that it takes some number of chunks as an input, but it rather than producing a single stream out, it produces two streams. So it both resolves upserts and then applies deletes, but then splits the output stream into rows that have timestamp prior to a particular time and rows that are after. And the lifecycle policy manager uses that to ensure that we're minimizing overlap between chunks that get persisted, to try to minimize the number of times you have to merge Parquet files. So those are pretty simple. Yeah, so as I mentioned, all the front ends generate plans, logical plans. So I'm going to just show you what the logical plans are for compactlet. It's pretty simple. It's literally just a table scan, like I showed in the SQL plan, and then it does nothing else. But it uses all the same machinery for all the other types of operations to apply deletes and upserts and stuff. But the actual planner for this is very, very simple. Split plan is slightly more complicated. It has a scan at the bottom, but then it has a stream split thing here. That's a new relational operator we added using the data fusion extension mechanisms. So in this case, it just takes the input and implements the logic we need of evaluating whether the timestamp is before or after the split time, and then segregating generating two output streams. So that's all it does, but I think it's a neat illustration of using the data fusion extension mechanism. Like, this is a very IOX specific sort of operation. It's not in data fusion, but we can add it fairly easily. Yeah. So now we'll move on to, I don't know how many people I still have with me, but we'll move on to the most interesting part of IOX, I think, in terms of integration into the existing InfluxDB ecosystem, and that is what's called the storage gRPC frontend. Right, this is also kind of where the sausage is made of mapping, for our vision of using IOX as the back end for the existing ways people are evaluating queries against the data stored in the InfluxData model. So in this case, there are two possible ways that IOX can get queries. They can get queries either from the Flux runtime, right? So Flux is InfluxData's scripting language that's designed for time series evaluations, or also InfluxQL, which is the sort of time series flavored variant of SQL that InfluxDB supports. Both of those under the covers are able to talk to the storage engine using a request called the storage gRPC format. And so that is both the existing TSM engine talks that way, but then also we're implementing the same thing in IOX. We're actually in the process of making sure that the responses are exactly the same for all the different operations. So that's been very deep in this last couple of weeks. So just like the other operations, IOX will then combine data in the object store and the various in-memory buffers like the read buffer or the mutable buffer, generate the response, and then stream the response back using gRPC in the way that Flux or InfluxQL responds. So this is the use case for the gRPC storage gRPC frontend. So to give you some amount of depth, here's a list that I totally ripped off from Ed, off one of the tickets. But this shows you the actual storage gRPC operations or calls that can be made to different APIs. There's 3 of them that are data queries, so like that are actually returning sort of raw time series data or aggregated or grouped. And then there's a variety of different metadata queries. Like, so here's an example. You can read the filter, read group is grouping push down windowing aggregates. Then there's a bunch of what are effectively metadata queries. So tag keys in the InfluxData data model are columns, right? So this is basically a way to get all the column names. These are tag values, a way to get the values in a particular column. And there's also a way to get the field. So that's another type of column. Now, one of the interesting things about these metadata queries that's different than traditional SQL metadata queries. Like, so traditional SQL metadata queries like show me all the columns in a table, and it'll just show you all the columns in the table, and that's that. These storage metadata operations will also allow you to put a predicate on it. So the equivalent is show me all the, let's say tag keys, right? Show me all of the columns that actually had data matching these predicates. So the common use case is show me all the tags that are available within this time range, right? Like within the last day, which hosts have sent me information or something if you're in a monitoring use case. So that makes it quite a bit different than traditional SQL metadata queries, because they actually sometimes have to touch the data. So, however, they're still incredibly common, and they get, not only are they very common and they get often done, they're used to drive UIs, right? So as you're using a UI to interactively explore the data, what's actually happening on the back end is metadata queries are getting issued and run against the storage system. So in this case, for example, measurement names, like if you've ever used the Influx Cloud or InfluxDB IOx Query UI, you'll see like the first thing when you go to explore your data is you get a list of measurement names, right? And so that's being driven by the response to this measurement names API. Tag key is the same thing that's used to populate a drop-down list, as are the values once you pick the tag. So the way IOx handles this, because they're so fast, because they're so critically important to return quickly, is that there's a fast pass. So the metadata query comes in, it can have an arbitrary predicate. It almost always, well, it often, especially when driven by these UI queries, has a fairly simple predicate, like within a certain time range. And so there's a fast path for those simpler predicates that exist. And so the query planner is responsible for detecting when the predicates can be answered with the optimized path, and if they can, using that optimized path in a chunk directly. And when they're not able to, the query planner is responsible for generating, a general purpose plan that can evaluate whatever predicates that might be able to take advantage of some of the special performance optimizations in the read buffer, or maybe it can't. But in either case, we still have to produce results. So this adds a non-trivial amount of complexity to both the read buffer and the query planner, but we think it's worth it given the use case for metadata queries. Cool. So now I'm just going to show the plans for tag keys and some other sets or some other queries. I don't really expect many people to follow along all the details here. I just wanted to give you a flavor of what these things look like. And I'm going to use these as then the gateway into talking a little bit more about the lower level physical plans before I wrap up, hopefully before too many people have lost interest. So here is an example query that might come in as tag keys. So you might get a tag key request that says, tell me all of the tag keys, so all the tag columns that have data that either has the value in the CPU column, sort of ends in the string total, or is within this and is within this timestamp range. And so, if you can see, a lot of these logical plans now become very repetitive, right? Because they almost always start with a scan and a filter, right? Like that's a huge amount of what a database does, scanning and filtering. So this also has a scan and a filter. It scans the CPU table, applies this filter that we talked about. Again, I'll talk a little bit more about it in a moment. But if there's special handling for these predicates in the read buffer, which actually there is for time predicates, those will get pushed down into the scan. And then we've got this fancy schema pivot here, another example of the data fusion node, which this is the thing that has the logic that detects, like, if there's any input that was non-null, it'll output the column name. So if you think about it, that's not a common relational operation to take a table in and produce a single sort of stream of column names out. So we use the schema pivot extension node, same hooks, not built into data fusion. It's all in IOx code, but we use those extension points, and it works pretty well. I also want to point out something else that's interesting about these metadata queries is they can affect multiple tables or multiple measurements in InfluxData parlance. And so, in this case, you can get a request to tell me all the columns, right? Tell me all the tag keys that exist across all your measurements with whatever predicate you want. This host, what possible measurements do you have for some particular host would be an example of why you might use this query. So in this case, what I actually do is actually make several different plans and union and merge the results together. Makes, for example, if we had maybe a CPU measurement and a memory measurement, and we didn't necessarily know if there was data for host in there, we'll run a plan to try to figure that out. And maybe there was another table that we were able to determine that actually had no data between the particular timestamps of interest. The query planner is capable of realizing that and then passing through basically none or not even running a plan for it. So save a lot of work. Same thing is actually if you could answer the query using one of the specialized read buffer paths that I talked about, just produces a list of strings directly. You could feed that as well. And then there's a code that goes and combines the results together up here. Read filter is another one of these gRPC queries. I'm going to go through this one quick because I want to have some amount of brain power left to talk about the physical plans. But a read filter plan, right? The read filter is what's pulling raw data series back, and it looks almost exactly like a SQL plan. So in this case, read filter says, tell me all the data that matches this particular predicate. Interestingly, because of the sort of flat InfluxData data model, the predicate contains like restrictions on both the possible table name, so the measurement name in this case. In this case, so it comes looking like sort of a special tag equals system. So that means I only care about the system table, and tag equals F. So this is a way to like basically do a column restriction. I only want the column usage user, and then I'm gonna check this tag is equal to that. So the InfluxDB gRPC planner in IOx will then turn around and translate a predicate like this into some combination of filtering and projecting down just the columns that are needed. It's also important to note there's a sort in here that I'm not going to talk a huge amount about, but this is very important because both Flux and InfluxQL expect the series to come back in a certain way, like basically the series to be ordered on tag key. And so here you can actually see the Influx, because IOx might or might not have the data sorted that way, the gRPC planner has to resort it in the way that Flux expects. So I think I talked about all this stuff. Yep. Cool. This I'm just going to show really, really quickly. I just wanted to point out for a physical plan, which I'm going to talk a little bit more in a second. Right, here's the logical plan. If you saw the data fusion talk, you'll know that the procedure goes logical plan, physical plan, then sort of actual execution stream. So the physical plan is like one level down. And so in this case, I wanted to show what happens for a read filter plan is that basically using all the mechanism from data fusion, that we have the projection exec and a sort, which all come from the corresponding logical plans. And then there's effectively a tree that gets created for each one of the sets of chunks, which I'll talk about in a few moments. But the Influx query engine is responsible for grouping chunks sort of in optimal ways, and then running them through different sets of filters, right? And the reason I say different sets might be because, for example, the delete predicate might be is applied per chunk, so you don't necessarily want to apply the same delete predicate to all the data, just some of the data. Yeah. So the point is, this all gets made, data fusion gets added, adds a bunch of stuff, and that's how multiple chunks get handled. But I'll talk about this more. This is details. It's probably not relevant. Read group. I'm also going to whip through this real quick so we can talk in a little bit more detail about physical plans. But in this case, read group is the way that Flux does grouping push down into the storage engine. It allows both aggregations on series and then as well as grouping the output in certain ways. So again, without trying to explain how all this works, if anyone's actually interested, I'd love to tell you about it, but I also don't want to spend too much time going into details that are just gonna, already probably over most people's interest level. So, again, these plans look similar. You scan, you do the filter, right? That pattern appears not time and time again. In this case, then there's a special grouping operation to actually compute the aggregates requested. In this case, there's a first aggregate, and there's a sort of special code that goes and figures out how to do first. Then again, we have to sort based on the order that Flux expects, and then there's a projection to make sure the column names are correct. All right, so that's read group in like 30 seconds in a way that I don't expect you to understand, but there's a point here that there's a logical plan, and there's a reason I've been talking all about just logical plans pretty much now, and that's because all of the different front ends produce logical plans, and then this execution plan stuff I'm about to talk about is shared by all of them, so that they're not, if the special cases execution plans for the different types of queries. So same thing works for SQL and gRPC and Reorg planner. So let's talk about how you read data from a chunk. So I think I've talked, or from simplest way, right? You've seen this sort of light blue box appear in a bunch of the previous slides that represents scanning data out of a table. And I've called it logical plan a lot. Then there's a darker blue node in the case where there's just a single chunk that has no deletes or any possible updates with other chunks. That gets translated, this one CPU table scan gets translated into something called a read filter node, IOx read filter node. It has a list of chunks attached to it. And then when that gets actually executed, that turns into 2 asynchronous streams. So you've got a stream down here that is specific to the type of chunk being read. And then you've got a thing called the schema adapter stream, and it produces the output. Now, what's the schema adapter stream, you might ask? I'm glad you asked. What it is a way to handle the fact that the InfluxDB data model allows you to do schema evolution. So schema evolution is a fancy way to express the concept that you might add new columns for new data, right? So you might originally record with maybe just host your output data. At some point, you want to add like pod name, or you want to add region or something. So also new data has this new column. The older data didn't. As we mentioned before, IOx doesn't have a fixed schema, nor does it rewrite historical data. So it might very well be the case that you have older data that has, or you dropped columns, right? So old data from different chunks might have different sets of columns. They have to be compatible. Like you can't have the column with the same name have different data types in different chunks, but they can definitely, there might be a column that doesn't exist in any of them. So the schema adapter stream is the specific mechanism that we use to make it so that the rest of data fusion, and all the other types of query plans I just showed, see a consistent schema out, is that it basically will null pad. So in this case, if the input has 2 columns, A and C, but the output was supposed to have also a column B, right? Because maybe a new tag got added and some other chunks. Schema adapter stream will go stick the appropriate sort of columns in there that are all nulled out. An arrow has a very efficient way to create these null columns. And then subsequent processing streams will just see a column full of nulls, even if that doesn't actually exist in the chunk itself. And I know I want to talk a little bit about something Ya has been working, from the team has been working on, about real-time resolution of updates and inserts. So, one of the major design goals of IOx was that the storage systems were immutable, right? So once you created in now called a chunk, it never gets mutated. You might read it, you might write a new chunk, you might delete entire chunks, but you never modify individual chunks. And that's a very classic way to do read optimized analytic systems. But if you do that, it has a lot of upsides. The downside, however, is that if you want to present to a user the ability to like logically update their data or delete their data, you have to handle, since you can't mutate the physical structure, you can't actually go modify those rows. You have to do it sort of at read time. And so that's what IOx does. So I'm going to show some crazier plans now of how we actually handle real-time resolution of updates, just to give you a sense of what it looks like, not necessarily for you to understand all the details. So yeah, even this is still pretty simplified. So in this case, let's assume that we had chunks that might have had overlaps. So for example, they have data that we can't tell from the metadata that they could potentially share the same timestamp and tag key set. So in this case, there will be, the plan will get built as we read the data out of the chunks, we then sort it potentially, depending on whether or not the original data was sorted on tag key or not in the correct way. We then combine the streams, don't get hung up on the fact this is union, it doesn't actually like put one chunk after another, it keeps the streams segregated. Then it runs it through what is called a sort preserving merge operator, which for those of you versed in classic database literature is your classic n-way merge. So it gets a bunch of different streams called data fusion calls them partitions, unfortunately, because it's a different concept than the partition of IOx, but you get a bunch of different streams, they get merged together, and the sort preserving merge ensures that the output is merged the same way, sorted still the same way as the input. And then we run it through a custom IOx node that implements the deduplication logic. So it finds rows where tag set and timestamp are the same, and squashes them together and ensures that the output row is what logically the row that was inserted last. Well, yeah. So that's how it works. So this is non-trivial expensive to do during operation. And a lot of the lifecycle policy managers sort of algorithm is designed to minimize the amount of time we have to do this. But the query engine is still responsible for doing this for any data that it requires. So, and so now sort of as a final piece, there's also deletes, right? So there's upserts, which are in the InfluxDB model. You can basically just keep inserting data, and if you insert new rows for the same timestamp of the tag, that effectively is modeling an upsert. You can also explicitly delete data. So for example, if you wanted to delete data that was older than the 1st of October in 2021, you would issue a delete command like this, and you give it a predicate. And then IOx, again, wouldn't actually modify any existing physical chunk data structures. What it would do is it would note in the catalog that the delete had been applied. And then at query time, it's now the responsibility of the query engine to apply those deletes so that users don't see any data prior to whatever they deleted. So the way we accomplish this in IOx is we'll stick, effectively the query engine now is responsible for sticking queries, filters in the same type of plan. So now you have a filter here, for example, maybe this chunk existed when the predicate got run, and then subsequently more data got added. So this chunk doesn't have the delete predicate on it. So in this case, the query engine needs to know and keep track of which chunks have what delete predicates, apply them. There's actually special case handling for faster delete predicates on other types of storage chunks like read buffer, the read buffer or the mutable buffer. And then it goes through the same type of thing where you scan and union and then sort, preserve, and deduplicate. So the actual sort of structure that will get built up for any arbitrary set of chunks is actually can be pretty complicated, and then, like I said, there's this whole system called the lifecycle manager that's one of its main responsibilities is to try to avoid having to do these complicated plans as much as possible, especially for the big historical chunks. And I think, yeah, so I think I covered that. I think that's basically what I have. I know that's like a lot of low-level discussion, which might or may not be interesting to people, but I hope it was interesting. I've certainly had a fun time doing it.
That was awesome, Andrew. That was a ton of information. So, if anyone has any questions, please feel free to post them in the Q&A or the chat. We're monitoring both. I have a question for you guys. We've been doing these InfluxDB IOx Tech Talks for almost a year now. Paul announced IOx last October, and I was just curious for all of you, what are you excited about? You guys have done a ton of work in the last year, and what are you excited about for the next 6 months or so?
I also wanted, before I answer that question, I also wanted to mention how cool I think the InfluxData open source philosophy is. Right. So these talks, like this talk I just gave, for example, I've given versions of some, talks with similar types of content in other jobs, but they've all been for just internal consumption, right? So it's basically designed for internal audiences. And so I think I at least am very excited the fact that it's all open. Now I don't know, how many people actually in the world will, take advantage of this knowledge, but the fact that it's out there, I think it's just really, really cool. And I'm, I can't wait to see someone take advantage of this someday and see some of these ideas either appear in contributions to IOx, hopefully, hint, or perhaps, in other systems as well.
Awesome. So Andrew, what excites you for the next 6 months or so, given where you guys have already come in the last year?
Yeah, so I think IOx so far has been like, it's in like the vision, it was been in the visionary phase for the last year or so, right? Where like Paul had the vision, I think he did a great job pitching it and explaining it. And then we sort of implemented enough to prove that it was feasible. And now in the next 6 months to a year, I think what I'm really excited about is seeing IOx turn from like a initial prototype, right, which has very little sort of production traffic to sort of battle hardening it and actually having it being used by a significant number of customers. And I think we're in that transition period now. And that's, that period is always, it always takes longer than you hope. And it's like, you got to spend a lot of time worrying about details, and it might or might not seem all that interesting at the time, but like it's a really important time in the life of a project. And so I'm very much looking forward to seeing the fruits of that.
Yeah, and Andrew, you've worked on other databases before in the past, right?
Mhm.
So what do you think, obviously InfluxDB is a time series database, but what do you think the impact of InfluxDB IOx will have on databases in general?
I think one of the key things that's interesting about IOx, InfluxDB IOx, is its use of open source, and like all this sort of query planning and stuff I was talking about. There is some of that that's specific to time series, but a lot of that sort of like what I would call sort of best of breed or state of the art sort of database optimizer, database technology. And so it's very cool to me to see open source projects like Data Fusion and Arrow effectively bringing what was state of the art in research literature, and then also closed source commercial systems. They're bringing those same ideas into the open source ecosystem and then being applied. I think it's a very, very powerful sort of idea. It's a cool thing to be a part of. I mean, I only touched on it like with one line and one slide, right? But the standard set of optimizations that Data Fusion has is pretty substantial, and it's only getting better, right? Like, and that's a lot of sort of the value of, it's great that it's not IOx specific either, right? So we're able to contribute back to the open source community, but then we're able to then take full advantage of it in IOx. So I'm particularly pretty excited about that.
Yeah, I gotta say, for me personally too, it's amazing seeing all the contributions from the open source community and how much the InfluxData, our team works with the community so much. I've worked at other open source companies, and I think we definitely do value them, like genuinely value them, and are excited to work with them. So definitely. All right. Well, if no one has any other questions, I think we can end things early unless there's anyone else on the team that wants to chime in or anything else to add. Cool. Well, thank you, Andrew. Hope to see everyone next month. We hold these every month on the second Wednesday of every month. And we are excited to see you on the next one, and also excited to see you at Influx Days here in a couple weeks. Thank you, everyone.
Thanks, everyone.